Right. So welcome to the morning session today. I'm your new chairman because actually the Matthias couldn't make it here. And it's my great pleasure to introduce somebody who really doesn't need any introduction, in particular here on home turf, Raul Tempone. And he will talk, so our splendid host here today, and he will talk about combining hierarchical approximation with importance sampling, approximation and optimization techniques. Please, Raul.
Thank you very much, Christian. All right, so exciting times. Let's try to make this worth. I want to acknowledge all my collaborators through the years. I cannot put the whole list, but you will see when I start citing who they are, and some of them are here. So, and some of them are attending online as well. So thanks to all of you for making this possible. I want to acknowledge both the support from KAUST and my Alexander von Humboldt Professorship Award in Germany. That is much appreciated and made many of your projects of those that are here possible too. So let's recognize that. Okay, this is an overview of my talk. I'm a little bit over ambitious as usual, but thanks to Lorenzo, for example, I will not have to explain certain things, and I will be able to jump over that. So let's go to the first two basic um, cornerstones um, for my talk. The first is control variance and importance sampling for Monte Carlo. So let's concentrate first on control variance. This is an idea that is very simple, right? It's essentially sum and subtract the same quantity. If you have to compute an expected value of a given random variable, what you do is you sum and subtract the same quantity. Of course, you don't change the thanks to linearity, you don't change the expectation, but being a quadratic form, the variance does change, and there's an optimal choice for this beta parameter that is real valued. And if you do the things right and a certain inequality holds, then the method will actually provide possibly substantial diminishing in the computational work. Now, which are these quantities here? Well, the epsilon actually is how good, in relative sense, this guy can reduce the variance with respect to the original variance, the variance of the y here. Okay, so this is epsilon here is supposed to be really small, and it relates to how good the variance reduction is. This eta that appears here is O1 essentially, nothing too much to worry much about. And the theta that appears here and should also be relatively small is the additional cost you pay for simulating together the pair x and y instead of simulating y. Okay, so of course, to construct this kind of methods, you given the y, you have to have some a priori knowledge to choose an appropriate x, and if you do, actually things work quite well. This is actually the basis for Multiindex Monte Carlo and the other hierarchical sampling methods that we all profit from. Second thing that comes to the help is the so-called importance sampling. The first one was sum and subtract by the same thing. This is divide and multiply by the same thing, essentially. So what do we do here? Well, we have to approximate the expected value of y again as the beginning. Now I'm paying particular attention on the measure that one is using to sample here from, and I rewrite the thing in a slightly different way as before. Now, instead of writing the expected value of y directly, I write the expected value of under a slightly different measure, called a q, and here I just have to multiply times the likelihood factor or Radon-Nikodym derivative to compensate for the fact that I'm not integrating under P, but under Q instead. All right. And now what we proceed with is to sample a la Monte Carlo directly from here instead of doing this. Now you could say, okay, these look alike. How do we get any advantage from here? Well, this random variable here under this measure may behave slightly different than this one. And for instance, it may behave almost like a constant. In fact, if you look at the minimal variance you can achieve using this kind of method, okay, the minimal variance that you have is a product of two things. One is a difference, and this difference actually becomes very small if this random variable to begin with had a constant sign. For example, it was strictly positive or strictly negative. In that case, this can actually become 0. And if you choose the optimal measure, which is a daunting task, and in practice, you're not able to do it, but you're able to actually shoot towards it and be inspired by it and get something close, you can get actually variance 0. Now, there's another way where this can be small. This may not be 0, but this, right, like in this inequality, can be such that this guy is much smaller than this, the original variance, and then you still get a variance reduction. That, for instance, as we will see, is the case of stochastic regression networks, where this part is not 0, but this actually provides a variance reduction that is substantial. So summing up again, there's an inequality that tells you when this is better than the original sample, right? And again, it relates to the possible variance reduction you can have and the amount of extra work that you have to do in order to be able to sample under this measure and compute this likelihood factor as well. All right. So the main point of this talk is how to combine important sampling and the generalization of control variance, that is hierarchical sampling, in different contexts. All right, so Multi Monte Carlo is a basic tool that we all know essentially, and it has been explained before. Again, it is the generalization of the control variance, but without using this beta. Directly, we write a telescopic representation of an approximation that we want to the quantity we are seeking, right? This is the quantity we seek, expected value of S. We approximate it by some expectation of some quantity that is a refinement of some numerical method, right? And sufficiently close in bias. And now we rewrite this in this way, and we sample a la Monte Carlo from here. If you do that independently across levels, you get this estimator, and this estimator can have actually a substantial variance reduction, so that at the end, even by the extra work that you pay for computing in different levels, you end up winning against the original Monte Carlo sampling. To show that theoretically, when Giles and Heinrich introduced this, and there are some assumptions that one has to make in terms of weak error, essentially bias convergence, variance convergence, and the explosion of the work. If you have these rates, and these rates actually can be estimated in different contexts, that is a priori, or even just computing them numerically, you can actually predict what is going to be the rate of the multi-level Monte Carlo approximation in terms of complexity, right? In terms of computational work to get to a certain accuracy. You can do all the computation, of course. The work of Monte Carlo is this sum of the work across all levels, that is the number of samples you invest in different levels times the work per sample on each of those levels. And the important thing to keep in mind, if you have not seen this before, is that WL, right, grows as L grows as well, right? Because typically here, what we do is to refine, that is to increase the number of degrees of freedom as L gets larger, okay? So the idea here is that you reduce the M as W gets large, right? And you compensate for the extra work per sample as you go deeper. You can compute the optimal work by optimizing the number of samples here and get to a complexity work theorem that says essentially that provided that the variances decrease sufficiently fast, that is S, which is a rate of decrease on the variances, is sufficiently, is larger than the work explosion rate that comes from the work per sample that you have to invest on each level, then you can actually get this sort of magical result, which says that you can compute with Monte Carlo with a corresponding cost of a Monte Carlo sampling method, as if the cost per sample will take you just all one, even though you're actually refining, right? And although the mesh actually, as tall goes to 0, has to go to 0 in size, so the cost per sample is going to infinity. All right, so that is something very, very important. And even if you are not in that case, you still get an algebraic advantage with respect to Monte Carlo because of these extra minuses that is here in the exponent. And the constants here we don't discuss; they are more or less comparable, as you will see later on. Now, since I'm going to move on to variance reduction in combination with important sampling, I need to make a distinction here. There are some popular methods that are called unbiased versions of Monte Carlo. They work really well when S is larger than D gamma. They achieved also the complexity total to the -2. And the idea is that essentially they are based on randomizing this sum here and choosing some optimal probability mass function for sampling over limits. That is not what I'm going to do. It may be combined with what I'm going to say, but it's not what I'm going to do today. So questions related to Monte Carlo, for instance, how to choose the mesh hierarchy. Can we actually start reducing this geometrically? For example, we start with a coarse mesh, then we divide by 2, then we divide by 2, and so forth. Or we do something more clever. Well, we discussed that thing, and so that actually there are more general hierarchies than just geometric. How to efficiently and reliably estimate the variances? Well, that is important. These variances actually appear in the complexity estimate of Monte Carlo, and they appear in the optimal choice of the samples per level. If you don't estimate them correctly, you may destroy actually the complexity of the method. Therefore, you need practical methods that on the fly estimate these unknown parameters, and that is essentially why we created this continuation Monte Carlo. And can we do better, especially for large dimensions, when, for example, this D is large? You can see here that if you keep S constant and gamma is more or less constant, if you start raising the dimension, right, you end up in this regime, and you lose the ability to go here. Well, if you exploit the mixed regularity as Lorenzo was talking about yesterday, you can come up with multi-index formulations for multi-level for Monte Carlo, and also for other things like quasi-Monte Carlo and stochastic collocation. And therefore, there you can break this barrier and actually get rid of this D. All right, so there's also work that we did in adaptivity, combining, for example, adaptive discretizations in time with multi-layer Monte Carlo. And recently, you can see a poster now in this meeting. There's a work by our student Yang Yu, that maybe is here, maybe not. Yeah, there you are, Yang. And he's presenting a poster on how to do Monte Carlo for random PDEs using space adaptivity to deal with geometric singularities. That's also a cool thing, because we have to deal with log normal coefficients that essentially are unbounded, right? So this is not a trivial matter. Now let's go to the heart of the matter. We want to combine important sampling with Monte Carlo. So what do? We introduce a sequence of coupling measures. These are important sampling measures that we call nu-L. These probability measures correspond to the pairs that we sample usually in multi-level Monte Carlo. So this will be the joint measure of the couple SL and SL minus 1. That is, we wanted to estimate to compute the expected value under P of S, right? We don't have access to S. We are going to solve a PDE maybe and compute a function out of it, and then our approximation will be SL, right? And we will be sampling under an approximate measure PL, because we don't have access to P. Why is that? How is that so? Well, maybe we are solving an inverse problem, right? And the approximation that we are doing is just to sample out of the posterior or something like that, and therefore that measure will not be exactly known, and therefore I had to track also the error that we make there. But okay, we have this L here and this L there, and we're going to telescope. So let's go on telescope, corresponding to both approximations on the random variables and the measures. Okay, so we do this. There's no change of measure still, and there's no coupling yet. I mean, these are just the marginal for PL, right? Marginal PL minus 1 for SL and SL minus 1 correspondingly. The first level, of course, is not going to be coupled with anybody, but we can still make a change of measure here, because as we saw from the beginning, right, important sampling may still help to reduce the computational work on this. For the others, though, I have to be a little bit more careful, because if I sample independently, say SL and SL minus 1, I lose all the coupling, there's no variance reduction, and the method is gone. So therefore, I have to choose this nu-L in such a way that this SL and SL minus 1 get closely correlated as much as possible. Okay, and this is not a trivial matter. In fact, if you look back at the cost of Monte Carlo and understand what is the contribution from this pair, you understand that actually, or maybe you remember that that contribution is the square root of the cost per sample times the variance corresponding to that difference. Therefore, the optimal choice of the coupling measure for a given L is to minimize this product, the cost of the sampling of the pair here times the variance corresponding to that pair. That's how you have to optimize to find this noise. This problem in general is difficult, but again, if you have a formulation like this, it can guide you towards trying to find approximate couplings that take you towards the right thing. Okay, so I write again the likelihood factors here, and the likelihood factors relate to marginals, right? Because PL was a marginal, so this is going to be a marginal of the coupling measure with respect to the SL, and corresponding here the other the other the other thing that has a missing D here, so there's a typo, but you understand what I mean. This is a Radon-Nikodym derivative as well. Okay, so now things look pretty straightforward, right? So for each method, you have to find out what is the optimal coupling measure and then try to get to the optimal complexity. And this automatically will take care not only of optimal couplings, but possibly rare events as well. So if you have something that becomes rare, automatically this will start steering the probability towards the rare event. So this covers everything essentially. All right, so examples. Let's begin with stochastic reaction networks. These are stochastic processes that actually are integer valued in principle. They are counting processes. They are used, for example, in chemistry, biology, queuing, and many other things, right? So the process essentially evolves in multi dimensions, right? And it is triggered by events. These events occur randomly according to certain propensity functions, and the representation, there's a curse representation, essentially is a bookkeeping that essentially counts the number of jumps that occur through independent Poisson processes. And there's a trick here that is a time stretching on the evaluation of these Poisson processes that link back to the X, right? So these Poisson processes are just, integer values. So there will be 0, 1, 2, 3, and they're counting the number of jumps of a certain type that occurred. And these new J's are the stoichiometric vectors that tell you exactly what happens when one of such events occur. For example, you're counting on a queue, a person arrives to the queue, that will be a +1 if you're counting the number of people in the queue, or if somebody is served in the queue, it will be a -1, and that will entail another reaction, right? So the arrival of the queue may have a certain A, and the serving of people in the queue may have another A, and so forth. So these J's is the number of reactions in the system, and you have to track them all to approximate the X. Actually, we are not looking after X, but we are looking at the functional at of X. So we may compute an expected value of some function of X at final time. That's what we're after. And well, as opposed to other cases, right, you can invest sufficiently amount of work and actually produce exact pathwise, evaluations of these processes. So in principle, you shouldn't need to introduce a bias, but you introduce a bias because it is convenient to reduce the computational work per sample. What happens here is the following. I mean, if you have a system that has too many reactions happening per unit time, right? That's a lot of computational work to track them from 0 to final time. So you may as well try to lump some of these reactions, right, and produce some approximate method that per unit time will take much less work. And since you already have not only the bias error, but the statistical error, you can increase the bias error without increasing much the total computational work. And in that case, you can get reduced complexity. Okay, so the way to do this, the way to lump, it is a forward Euler method version for this kind of systems that is called tau-lip, and it uses Poisson random variables with certain rates that are frozen exactly like Euler would do at the beginning of each interval. All right, so this is the mathematical formulation of this system, but I already told you more or less the intuition. What is the problem here? Well, the problem is that, like I told you, these systems are integral value. Okay, so you have a sort of forward Euler-like method, and it's going to converge to the right thing. How does it converge to the right thing? Well, you take integral values, right? So it's not like you're going to get 0.5 close to the other and then 0.25. No, it is either you're equal or you're 1 plus 1 away, say. Okay, so what happens then for these conversions to occur is that the probability of being different goes to 0, right? So uh, if you start looking at the multi-level Monte Carlo differences, what happens is that the probability of them becoming 0 gets higher and higher and higher. How large? Well, it is 1 minus of delta t, right? So as you start refining the delta t, you will observe that most of your Monte Carlo differences are 0, and only few are, say, +1, +2, or -1, or so forth. Well, if you're computing an expectation of such a random variable, that difference, that is essentially a rare event, because most of the time you're 0, and then very rarely you become 1. Okay, that has, of course, some alarms to take care of, because you don't want to deal with a rare event without introducing important sampling, right? Because you will be very inefficient. In this literature, this is called catastrophic coupling, because things look really good because the things are 0, but you're missing essentially the point, right? I mean, you're missing the important part that actually gives you the expectation for that. So you have to change the measure in such a way, in a clever way, so that actually this doesn't become so often 0, and you can still compute things without blowing up, for instance, the kurtosis of this random variable. And this is important because, again, why do we care about kurtosis? Because the kurtosis essentially is related to the variance of the variance. So if you want to estimate, like I said before, the variance of the differences, and the kurtosis is going to infinity, you're in bad shape, because you're going to have to use a lot of samples to estimate accurately the variance in multi Monte Carlo, and that will destroy the method essentially, because the kurtosis is blowing up as you get deeper. So you would like to use less and less samples, but you need to use more and more to be able to estimate the variance accurately. So that's not okay, and we need to introduce the variance reduction of important sampling type because of this. Okay, so that's what we did in this work. We introduced a change of measure in the levels, right? So this thing does not catastrophic coupling as before. So we have some theorems that actually show that we can actually reduce substantially the kurtosis, but I mean, we didn't expect that at the beginning, but it happened actually. We got an additional rate on the variance convergence, this delta here, and delta can be between 0 and 1. This delta actually pushes us into this 12 to the -2 case, the optimal case, in this setting, and we get rid of the non-optimal log terms. And in practice, right, if you go and check what happens with and without this important sampling, you get, of course, the optimal complexity. You reduce the kurtosis, and you can go and verify. For instance, I put one example here. You can verify what we predict, essentially, that if you don't do anything, you just run this happily, right? That's most of the literature showing, right? You will have a certain rate in the convergence of the variance, that is just rate 1. You will have an explosion on the kurtosis. Here you see that it's going from essentially 0.1 to 10 to the 3, which is brutal in terms of kurtosis, right? You have a certain cost per level, right? And this essentially brings you to some complexity. But if you use the importance sampling at essentially the same cost per sample, you get a better rate of convergence for the variance. Essentially, now the kurtosis is bounded between 1 and 6, right? So it's not 1,000 anymore. It's just essentially bounded, and you didn't increase much the cost per sample. So this is really a big win here. We achieve the complexity with almost no cost, additional cost, and we can see the advantages with respect to the standard multi-level Monte Carlo in terms of cost as well. Now, I want to point out here to a new work of us and our student Sofia Disha, who is here. Sofia, say hello. Yeah, she has a poster on how to do in this um, stochastic regression network framework important sampling using stochastic optimal control techniques. And that relates to essentially level 0 in this discussion. So what we will be working on is a combination of these two techniques, right? The stochastic optimal control for the first level and the coupling for the others as well. So that is where we are going to, and we are very excited to go through. So now I'm going
Raul,
to switch gears. Please.
may I ask a question?
Yeah, absolutely.
So first, why is high kurtosis a problem? And second, could you also maybe motivate a little bit how you actually do the importance sampling in this case?
Yes. Okay. So why is high kurtosis important? Because first of all, the number of samples per level is chosen more or less according to this formula that I'm marking here. And what you see here in blue are the variances corresponding to the differences of that level. Now, what is the variance of the variance, right? What governs the Monte Carlo estimator of the variance? That's the kurtosis. So if the kurtosis is blowing up, the relative accuracy that you have on these variances is deteriorating substantially, and the number of samples that you need to estimate this in a relative sense accurately is blowing up, right? So to have a kurtosis that is southing versus a kurtosis that is just 6 is a huge difference. And that's why we care about that thing, because as I said, you really need to have, for optimal complexity, the number of samples decreasing. But if, and you have to choose them according to the variance, but to estimate the variance, you have variances that have, sorry, samples that have to be blowing up because of the kurtosis, then the whole thing gets broken, right? So unless you have a super sharp variance estimate from the beginning, that is a priori, you're very in trouble, right?
This is basically because you kind of adaptively choose the number of samples based on the variance that you
Yeah, I mean, in Monte Carlo you need, so what you would expect here is that that the variance the variance is being reduced by, I mean, according to delta t, the number of samples should also decrease like delta t, but the kurtosis is blowing up like 1 over delta t. So that's really not good. So that's why. Is that okay? Okay, cool. Great. Good question. Okay, so let's go back and switch gears. So, you know, Lorenzo was showing.
Sorry.
Yeah, tell me.
That was the second part of the question about if you can motivate how you choose the importance sample.
Yes. Okay. So, what governs the evolution of the system are these rates, right? So these rates actually are the ones that that actually govern if you're going to jump or not. Now, what happens as you go with delta t smaller and smaller? The two approximations, XL and XL minus 1, get A's that are too close. They indicate that actually they're going to jump in the same way. So what we do essentially is we use this coarse representation, and we have two components for the jump. One that corresponds to the base A, say, and the other corresponds to the difference. The one that corresponds to the difference, we're going to tilt, and we're going to introduce a different rate. And this creates a likelihood factor, but this rate now will allow us to make the jump more likely. So what we do is essentially the following. We start trying to introduce this jump. So you start from 0, the guys start at the same position, the A's are the same. So maybe you try to do this and you don't succeed, they still remain equal, both levels. So it's like a geometric, right? You try, and suddenly you succeed. When you succeed, the likelihood of them getting again together is very low, and essentially you can forget about it. So what we conclude essentially is that the number of tries that we have to make is not so large, right? So we can actually control what is going to happen with the likelihood factor that you introduce. It will not produce a blow up, right? So this is this balance, right? And the good thing that actually happens here is that yes, you have to try, but you don't have to try for many components, and you don't have to try it many times. So the likelihood factor is under control, and then you get the variance reduction. So we use the Kurtz representation, right? Heavily to tilt things. It's not the only way to do it all, but that's what they did there. There are other ways to do this too. Okay, that comes for the future. Thank you, and don't let me go if I avoid one of your questions. Thank you very much. Okay, so let's go to the PDE motivational example. Lorenzo went through these things. So you have a PDE, it has random coefficients. You want to compute some functional out of the solution of the PDE. What do you do, right? Well, you try to use Monte Carlo the same way, but you can also do multi-index Monte Carlo. You can do multi-index stochastic allocation and so forth, right? He went through that yesterday. I don't need to go through that today. The main point that he tried to make also is that you don't need to work with very particular meshes. You can adjust these ideas to different domains, and provided that you have the right mix of regularity, you beat multi-layer Monte Carlo big time, particularly in large dimensions. So, and you can actually, you have techniques to show that this mixed regularity exists, and you can extend to even sparse kernel approximations and so forth. So let's jump over this because he talked about that. So let's put a word here because I want to make a link to another work that is on the poster session. We also work with multi-level and multi-index Monte Carlo, but in this context for stochastic particle systems in mean field. So these stochastic particle systems may be modeling, for example, a large gathering of people, right, or sort of particles in a flow, moving in a certain domain. Or here, for example, we are trying to model people trying to escape from a certain situation and try to put an obstacle here near the door to actually help guide the flow and not I mean, you would think maybe at first thought that this obstacle may complicate the exit. Actually, putting obstacles in the right place may even help to avoid the high pressure points, right, and trampling over people. Anyways, so this is why this is important. It relates to the so-called McKean-Vlasov equations. And using multi-index Monte Carlo without changing the time stepping method was able to reduce the accuracy, the complexity to achieve a certain accuracy of order tall that was 10 to the -4 up to essentially 10 to the -2. So no change in the discretization, just change on the way you sample provides that huge reduction. Okay, so that's if I can actually click here. I don't know. I mean, it has been so much time without using Windows that I felt so awkward using Windows on Mac, right? So I don't know how to click this thing, but it doesn't matter. What really matters here is that Sean Mohan, who is over here somewhere, yes, there you are, is presenting his master thesis in a poster showing how to do important sampling methods for McKean-Vlasov stochastic differential equations. So that's another good work that is connected to this. So you can go and discuss with him. I don't need to give you details. So multi-index collocation is what Lorenzo was talking about yesterday. It provides big advantages, and you can actually show results even in infinite dimensions. We work with Lorenzo also and Joachim on this multi-index stochastic collocation with isogeometric analysis to push these things into broader geometries. That is not needed. And the next point that I want to make is another way to motivate important sampling in the context of hierarchical approximation. So first, we did this example on catastrophic coupling, right? So we wanted to avoid things getting too close, right? And we have to separate them a little bit to get optimal rates. Now here we have to compute the expected information gain. We are trying to do optimal design of experiments. So essentially, you want to learn about certain parameters. You have some prior knowledge, which is a prior PDF about these parameters. You provide some different choices of experiments, that is different likelihoods that you're going to do to learn about these parameters. And your objective is actually to choose the best likelihood, that is the best experiment, to somehow reduce the uncertainty in the optimal way in the posterior, right? So this is Bayesian setup. So how do you formalize that cartoon description? Well, you say, I want to compute the expected information gain between the prior and the posterior and maximize it. So itself, the expected information gain, it's a nested expectation and has some measured concentration that complicates the Monte Carlo sampling. Um, there's a series of work that I'm citing here with some collaborators that are here. Joachim, Luis is not here, but Ben Mansour, I think, is here too. Yeah, at least he was yesterday. And Chuan, that is now in US in Honeywell. Um, so I want to point out that Arved, who is here, yes, there, that is also a PhD in LVTH, has a work on small noise approximation for dealing with a slightly more general thing that I'm going to talk about, a case where actually we have nuisance parameters that we cannot learn from. Okay, so throughout the Bayesian update, we have to keep the uncertainty for these parameters essentially constant, and they require extra integration, and that is what we deal with in that recent manuscript. Okay, so let's try to show you what this is about. Essentially, you have a data model. Here we have additive noise; it's just Gaussian. Now, when we have this model, the model depends on a parameter. The parameter is theta. The psi here relates to the setup of the experiment. So different size means different likelihood, different experimental setups. And what we want to do is, for a given psi, be able to compute the expected information gain, which is just some kind of multiple integral here, right? So this contains some logarithm connecting the likelihood here and the evidence and some likelihood here as well. Now, we do here, we can just plug multi Monte Carlo approximations and get a double loop Monte Carlo approximation that we cannot just put into a single loop, because we have some nonlinear term here acting on a conditional expectation. So we need to deal with this nested expectation. What we do is to introduce important sampling and multi Monte Carlo to accelerate this computation. In fact, we not only do Monte Carlo, we did stochastic allocation, but it's important to introduce the important sampling. Why? I mean, when you see this formula at the beginning, you do not see why. Where's the problem? When you write it, you rewrite it a little bit differently. You get to this term here, and this term actually is related to the number of experiments that a setup can introduce. And what happens with this number of experiments is that it makes this A, essentially, you see there's no balancing 1 over n here. Essentially, when you start adding terms, right, this gets larger and larger and larger. In terms of Gaussian approximations, right, this means concentration, right? And concentration means, in some way, some kind of need of important sampling, right? You're trying to estimate the expected value of something that is becoming picky, really picky, right? Concentrating in a certain place. So that is why you need important sampling, because otherwise you can get into underfield computations and really nasty stuff, of course, losing the amount of work that happens when you just sample without important sampling in such a cases as well. So that is something that you don't want to do. So you introduce important sampling. In this case, important sampling is guided by a Laplace approximation. There are assumptions on convergence as well. I don't need to go into that. And once you do this, you do this computation using the Laplace approximation to create an important sampling that tracks essentially this concentration effects. Then you can get a substantial reduction, say in the, well, here there's an example of this Carlon computed. Actually, Carlon, you're there also. It's one of our collaborators too on these works. You can get a substantial work and so substantial reduction in uncertainty from the red, which essentially is a posterior without choosing properly the experiment, and the blue, in this case, reduces substantially the uncertainty in the posterior. And this is a sum of that. Okay, so these are examples. We did computations, we checked the errors, and we compare methods, and you see that using important sampling, even in the context of Monte Carlo and then stochastic collocation as well, you can get a substantial reduction compared to the methods that do not use these tricks. Okay, so the first was catastrophic cancellation. The second was a concentration of measure that we have to trick to deal with. The next one is a hierarchical approximation that in some sense connects to machine learning as well, is regression problems, right? So this is an L2 regression. You still have a PDE behind. So you want to compute essentially the response function of a quantity of interest with respect to a parameter y, right? And you want to approximate it not just in the sense of the expectation of the q of u of y, but you want to compute the whole function q of u of y. Okay, so what is the straightforward thing to do is to just put the loss function, right, and try to find which is the best approximation you can do with this q. In this discussion, I'm going to use polynomials, right, but you will see that this can be generalized as well. So our goal here, at least in the presentation, is to approximate this function by multivariate polynomials of y. What is the thing that pushes us into using hierarchical methods? Well, is the fact that we don't have access to the solution of the partial differential equation. Therefore, we have to use some approximation. Therefore, if we sample less in deeper levels, we are going to get a reduction in the work and still be able to achieve the same accuracy. All right, so what do we do? Well, again, we have to create a appropriate subspace of polynomials to project on. That's downward closed, as Lorenzo was explaining yesterday. And what do we do actually in practice? If you don't want to do any hierarchical approximation, you will just sample m points in the space of the parameter, right? You may use some important sampling, so you have to compensate by introducing the Radon-Nikodym here, derivative. Once you have this weight, you go and compute your regression in your discrete L2 regression, right? Having this sum, and again, in the sum you compensate with the weights that correspond to this Radon-Nikodym. Okay, what happens with this discrete norm square is actually that its expectation is unbiased with respect to the L2 norm you would like to minimize. That's a good property. We have to solve again the algebraic system as usual for the least squares with this Gramian matrix, right, which has a discrete product of the basis functions. And there's a theorem by Cohen and Migliorati in 2017 that introduces that has the right sampling inequality, and this sampling inequality connects the number of samples that we need to project in a stable way over a certain subspace with the number of the number of dimensions that subspace has through this sort of obscure k number here. This k number is the supremum of essentially the sum that you will have to integrate for the L2 norm, but now estimated in L infinity essentially, right? And you still have this weight here. So this is a quantity that depends on the subspace and the weight, essentially, nothing else. I mean, it may look like it depends on the basis functions, but actually no, it depends on the subspace. If you are given this, then you can choose the number of samples, forget about the log really, so that actually you have a stable recovery. And by stable recovery, we mean that the Gramian will be sufficiently close to the identity, and therefore this condition number will be controlled and everything will go fine. And this happens with large probability. And what is here behind essentially is the theory of large deviations for matrices. That's what is here behind this result. So provided that you get this number of samples, then you can get with high probability the same L2 approximations that you will get for the true L2 with these discrete methods. Okay, you pay a little bit of a price here, but it's not really substantial. Now this result uses exact samples, right? So you have a function, you sample it exactly, and then at random points, say, and then you produce a reconstruction. And there's no multi-level here. There's in principle perfect evaluation. What happens if you introduce a multi-level? Well, here again you have to introduce a sequence of functions that will approximate, and this will correspond to your finite element or finite volume or whatever. And we put here the number of degrees of freedom or some kind of index that indicates that you're refining, right? So as you refine, this approximation gets better and better. You have also the corresponding subspaces of polynomials that are actually getting larger, and through that you get also good approximation of functions. And now you're going to combine the two, right? So in the multi-level formula, you essentially play the, the differences with respect to space with the difference of projections over, set of decreasingly unnested polynomial spaces here, and you can actually sum over one of the indices here and get sort of a more multi-level Monte Carlo formula where you have differences of more and more refined solutions of the PDEs, and then here projections that are becoming coarser and coarser and coarser. So this is funny the first time you see it, because in some sense you get more and more accurate in the PDEs, right? You're taking differences, but you're projecting on coarser and coarser spaces. And why is that so? That you need to project on coarser and coarser spaces and you get away with it? Well, actually, it's because this difference is going to zero. So because of the fact that you're trying to make an approximation of a function that is essentially going to zero, you need less and less polynomials to deal with it. Okay, and that actually is very convenient because now, since the number of samples in this context is just used for stability, not for accuracy, the fact that actually you have a coarser and coarser projection allows, because of the sampling inequality, to use less and less samples. So you have the same effect as in the usual multi-level, right? You have less and less samples, and you're going to win again because the deeper, more costly per sample solutions are sampled less and less and less. So you can again optimize the choice of the polynomial subspaces, the choice of the PDE refinement hierarchies, and you can get the results essentially. And the results indicate that, as usual in these sparse approximations, you're going to see only the worst of the rates, not just the sum of the rates. I mean, usually when you do tensor approximation, you get the sum of the rates. So it will be the worst rate with respect to the polynomials and the worst rate with respect to the PD. Here in this multi-level approximation, you only see the worst of it and you get rid of the other. Okay, so that is technical, but essentially what is important is, again, this lambda contains the maximum of the worst of the rates, not the sum of them like you would normally have in some tensor approximation that doesn't use this sparsity. Okay, so you can have applications on random PDEs again, and we confirm the advantages of the multi-level versus the single level version of this discrete regression. So as a conclusion, right, again, I invite you to use multi-level discrete least squares whenever you have to compute with output quantities that depend on random PDEs. That will definitely give you an advantage if you have enough regularity. We are using the combination technique to get an advantage of these things. And of course, you have to keep to be able to have these sampling inequalities to be able to ensure stable recovery of each of the projections that you make in this multi-level approximation. The complexity carries out on infinite dimensional problems. You have to use the summability theory. You have to go to this stretching lemma and the summability, but yeah, that's not the main point of today. So that's going to get technical. Now, how much time do I have? 8 minutes or so?
Yeah.
Okay. So I want to close just with something that is optimization. So this is a stochastic optimization. So in the context of machine learning, this will relate to learning. You have to try to estimate the minimum of a function, but this function is not given explicit to you, is given through an expectation, right? So an expectation may be a costly thing to have, so you want to get away with it without having to compute the expectation or approximate the expectation accurately at each step. Classical method, Robbins-Monroe, and the stochastic gradient descent. So you sample this theta, which is a random part here, from a certain measure, right? And you take a step on the create iterates on the side, right? Going through the stochastic gradient and getting a descent on that, right? So here, what you have to pick is this learning rate or the step size in the stochastic optimization literature, and the applications are all over the place. I don't need to go through that, right? This problem is very useful. And what we introduced was the multi-iteration stochastic optimizers, and those guys should not be confused with multi-level. Once I will write the formula, they look alike, but there's no refinement here. There is no PE, there's nothing. It's just a stochastic optimization problem that depends on this psi and this random thing. There's no discretization, there's no delta t, there's no h, nothing. But we are still going to produce control variates type of reduction because of the fact that if essentially evaluations of this f are done in nearby size for the same theta, right? They will be close, and those differences will be small in L2 sense, right? And that's what we're going to exploit. So that's why it's multi-iteration, because the reduction of the variance is done across iterates, right? And we're exploiting that things are close to each other and not close in terms of refinements. Okay, so that's one ingredient. The other ingredient that we use is to try to have a control, a relative control in the approximation of the mean gradient by some estimator that we produce, and that will be the MICE, right? The multi-iteration estimator of the gradient in this sense, right? I mean, there are technical parts, and Carlo is here with a poster. He can explain all the nitty-gritty details. But okay, we did it, and it works really, really well. We have theory that backs it up as well. So here's the estimator. You see, you have an approximation of the mean gradient done over different. I mean, here's a hierarchy it's a subsample of the previous iterates essentially, and you have something that looks very much like a multi-level, but Monte Carlo, but there are no levels of refinement, and these things are not independent. So these things have to be really kept in mind, because otherwise you think that this is easier than it is. So nota bene, this is not Monte Carlo. All right, so how does it work? Well, it is very connected to the so-called mini batches and big batches type of approach, right? You start in a point, you sample a number of samples, you produce a mean gradient, you take a step, then you go to the next step, and now instead of forgetting about this guy and moving across, we're going to still use this base point. We try to move to this point. We're going to sample differences here and sample the base here a little bit more, right? And then we go to the next, and so forth. Now, in the process, actually, you may decide to drop some of these iterates, and because you disadvantages, even though they decrease the variance, they increase the work, and this may not be so useful. So what we proved actually was that you have exponential convergence with respect to the number of iterations here, and this number I mean, this exponential convergence happens with respect to the condition number of the Hessian, essentially, in this way, much like in the iterative methods that you will use in numerical linear algebra, right? So you have this factor in those methods as well. But here, what is interesting is that the epsilon coming out of this relative error in the gradient control appears explicitly. So now we can play optimization here to get optimal complexity. Polyak understood that actually this relative long ago this relative error control in the gradient will yield exponential convergence with respect to the number of iterates, but he didn't work out the formula, and he didn't work out the optimization in terms of complexity, as we are going to show. Okay, so kappa again is related to the Lipschitz concept of the Hessian and the minimum, coercivity in that. So what about the numerical complexity? We have some theorem again that works out in this way. The expected value of the cost is going to be related to tol to the -2, where tol is the accuracy that you want to achieve in this event, right? Being close to the optimum. Here you have two condition numbers, right? One is the kappa that I told you before, and this kappa hat is the so-called, L2 approximation that we have coming out from these control variates, right? nearby essentially points, same theta, and you compute the L2 difference in the gradient, and you get this L hat constant, which is slightly larger in general than the L that I put before, right? So this is the other condition number that appears here explicitly. And now you see that the constants are very clean in the expected value of the cost. And yeah, the question is, okay, do we get something out of this? Well, if you go in practice, you see for very simple examples that in terms of the gradient evaluations, you win easily with respect to the stochastic gradient descent. You can go into non-convex cases like the banana function, the Rosenbrock, and in that case, combine the multi-iteration estimates with Adam, which is a very popular method in machine learning, right? And win over the standard Adam using just Adam combined with mice, even in runtime, right? This is the first sort of non-professional algorithm to compare the two, and we still win. And here's a case that is a logistic regression where we actually have good control on good estimates on the parameters of the Hessian, right? The maximum and the minimum eigenvalues, and we can more or less check the theory with respect to the practice. And again, for this Higgs set that contains 11 million data points, so this you can think of big data if you want, and the number of features that is around 30, we get a huge advantage, which with respect to a lot of SAG, Saga, SVRG type of well-established methods in this context, and not only in the number of gradient evaluations, which show the potential of having a very efficient implementation of this method, but already with this first implementation, we win in runtime, right? Fewer iterations, slightly less runtime, and that I think is where I want to close. I presented you this multi-iteration to bring a little bit the idea that hierarchical approximations may appear in the most unexpected places, right? So it's just up to your imagination to pull out what is the meaning of a level. And in terms of what is left to do in the combination of importance sampling with the hierarchical techniques, there's a lot to do. Yeah, these are exciting times and exciting area to work on. Thank you so much. Yeah.
Thank you. Are there questions?
Thank you very much for talk. Can you please say what do you think about surrogate models, polynomial chaos, stochastic Galerkin, where you decompose functions and bases and so on?
Well, this is very much related to multi-index collocation, right? So multi-index collocation can be interpreted also as using basis functions for polynomials, right? So in that case, even if you use either interpolation or regression, you may have to think of using some importance sampling if you have a measure of that will weight your error, right? So things can be combined with those as well.
Thank you.
Yeah.
Other questions?
Oh, I got this one. Thanks for the talk. So you said with the multi-level least squares approximations, you had that the projections were random. So you need to ensure that they're stable and convergent. And you said that the issue is you had to compute failure probabilities. You had to compute failure probabilities.
Failure probabilities.
Yeah. So failure probabilities of what in that case? Failure probabilities of what in that case?
Okay. Good thing. It is the event of the Gramian being far away from the identity.
Okay.
So let me see if I can show this to you. Okay. Weighted. Okay, here. This event. Failure is understood as the Gramian being far away from the identity. So we are okay if we're in this setting, because then we can control the condition number of the Gramian, and then we can essentially, up to a certain small constant, get the right approximation in the projection. And you see here, this is slightly modified projection is like this. if you have control on the gradient, you're going to take the projection that you get. If you don't, you just put 0, right? And this is essentially what brings the other term in the error, right? You get this essentially. That's the price you pay. And this m to the minus r is not a coincidence. Essentially, it's coming from this failure probability.
Yeah.
Okay.
Thanks. Yeah.
Is that fine?
Yeah. Yeah.
All right. So.
Okay. Another question by Alex.
I just repeat the same question which I asked yesterday, Lorenzo. He also
I don't
said
remember
that
the question.
So yes, assume that we have some diffusion, convection, diffusion problem. So what's going on with variance when I refine mesh? Is it always decreasing, or it also may increase?
No, I mean, you can have non-asymptotic behavior, right? So no, I mean, certainly when you get into the asymptotic behavior, you may get decreased, but there's no guarantee to begin with.
Okay, thank you.
Hi, Raul. Thank you, first of all, like really this comprehensive talk. Can you please comment on something like the use of this multi-level Monte Carlo with important sampling in Bayesian inference problem?
In
Bayesian inference problem?
Well, the expected information gain problem that I talked about, which is optimal experimental design, is one level above the classical Bayesian step, right? Because in that context, you have to conclude to talk about all possible data that you can get, right? So for Bayesian, you can still do it. I mean, there's work that we did for Markov chain Monte Carlo, and other contexts as well. So there you have to use important sampling too if you want to sample from a posterior that concentrates, for example, right? So and if it concentrates along manifolds and things like that, things are going to be more complicated too. So yeah, I mean, you have to take you have to at least aim to have a good control on the estimators for the relative variance, right? So yes, in that case, one has to try to do it as well. I have not talked about the inverse problems because time does not allow, but you have to try to aim to have a robust method that keeps control on the variance independently of the parameters, right?
So maybe a quick question, but otherwise I would ask people to ask Raul in person because
yeah, very quick one. Thanks, Raul. So it's very interesting, this important sampling appearing everywhere. Is this measure of important sampling also in some of the methods adapted, so estimated on the fly, like variances and all the other?
Yes. I mean, there are different techniques to do that. One of the ways to do that is to use learning and some, for example, ansatz. The ansatz could be machine learning type, could be different things. But what we did essentially was to connect, like you can go and talk to Sophia, right? This problem of variance reduction with stochastic optimal control. And that's a systematic way of connecting the two things, right? Because then you don't have to invent the important sampling. It comes directly from a first principle that connects directly to the second moment. So there is no, I mean, there's a way to do it, right? Okay.
Okay. So let's thank Raul once again.
Thank you very much.
And I suggest we have a short 2 minutes break in order to set up the new talk.